This section from the chapter on bone tissue and the skeletal system will concentrate on the homeostasis of calcium and how broken bones repair themselves. In the last couple of sections, we've been discussing growth processes, and really calcium homeostasis is an extension of that. The levels of calcium in the blood are regulated by hormones that help build up or break down bone matrix, both of which processes are taking place during growth, such as appositional growth. Before we get to the processes involved in calcium homeostasis, I want to remind you of the major cell types that are going to be important here. There are osteoblasts, which are responsible for building up bone matrix, which they do by secreting the protein-rich osteoids that help to incorporate calcium phosphate crystals into the bone matrix. And osteoclasts, those unusual cells that are derived from white blood cells and break down the bone matrix, releasing the calcium back into circulation. The processes of adding and removing calcium are always in a balance, and there's generally not a net gain of calcium in bone matrix because as it's being added by osteoblasts, it's being removed by osteoclasts. And when we see growth processes or a response to an imbalance in the homeostasis, those two processes are thrown out of balance. One of the main functions of bone that was mentioned at the beginning of this chapter is the storage of minerals, and the main mineral that we're talking about here is calcium in the form of calcium phosphate crystals. Now, there's a homeostatic mechanism that regulates blood calcium levels, and when there's too much, the calcium's stored in bone, and when there's not enough, calcium's released from bone. Normal calcium levels are around 10 milligrams per deciliter in the blood. When the levels go above that, that stimulates part of the thyroid gland to release a hormone called calcitonin. And the name of that hormone, calcitonin, actually points out that it's important for calcium concentration. Now, the cells that make calcitonin are called the parafollicular cells of the thyroid gland. When calcitonin gets into the bloodstream, it travels all over the body, but it targets the osteoclasts in the bone, making them less active. And by inhibiting them, the bone matrix gets built up a little bit more by the osteoblasts, which is going to take up the calcium from the blood. While calcitonin's active, the kidneys decrease the amount of calcium that they reabsorb from what's going to be the urine, which is also going to help the blood calcium levels decrease as calcium is excreted in the urine, and that should bring the calcium levels back down to a normal level. When the blood calcium levels dip below 10 milligrams per deciliter, then the parathyroid glands will release their hormone, which is referred to as PTH. That stands for parathyroid hormone, but we just refer to it by its abbreviation, PTH. PTH also targets the osteoclasts, and it causes them to become more active, which will break down more bone matrix and release more calcium into the blood. The PTH also is targeting the kidney, and that's what's causing reabsorption of calcium from the urine back into the bloodstream. When calcitonin causes a decrease in reabsorption, what's really happening is just that PTH levels are going down, so the calcium is resorbing less calcium. Through the kidneys, PTH also stimulates the small intestine to increase the uptake of calcium from the food that we're digesting. All of this is going to increase calcium levels in the blood and get us back up to the normal level. We also want to consider how broken bones repair themselves. It's really another type of growth process, just within an already mature bone that has to repair damage to the tissue. This figure demonstrates the general classification of different types of bone fractures. It's not a complete list, but it's a good idea of how different things happen. So a closed fracture is just a fracture where the bone remains within place. Open is referring to something that breaks through soft tissue, usually the skin. That's also called a compound fracture. Transverse is just referring to a break straight across in the transverse plane of the bone without the two halves of the bone separating. A spiral fracture is when the fracture is at an angle, sort of wrapping around the bone. Comminuted is when the bone fractures into a few different pieces at the fracture site. Impacted is when the bone breaks because there's force along the length of the bone and it pushes the two cut ends closer together. Green stick is when the bone doesn't break all the way across, and it gets its name from when you try to break a immature piece of wood, green stick. It'll just sort of tear a little bit into the stick. Oblique refers to at an angle. So instead of a transverse break, for instance, that's straight across, an oblique break is going to be at an angle. When a bone gets repaired, there's a standard set of changes that take place within this bone. Now, this figure demonstrates a fracture where the periosteum has not been broken through. For the sake of this picture, it helps to contain what's happening within a specific place. The periosteum is as likely to get ruptured in a break as not, probably. Now, the first thing that happens is a lot of bleeding. There are blood vessels going through the bone, and so they're interrupted by the break, and they're going to spill blood into that area, which produces a hematoma, or a collection of blood tissue. And that hematoma is going to eventually start clotting and covering up the break site loosely, allowing for the tissue to heal up. Within the break site now, the tissue is going to start healing by becoming two different types of tissue. There's the internal callus and the external callus. Callus is sort of a word we associate with a scar. This isn't a scar just yet, it's the healing tissue. The external callus is the remnants of the hematoma and some soft tissue that helps to protect the break site while it's healing. The internal callus is where the blood vessels repair themselves. Being mostly epithelial tissue, they do that very easily. And then soft tissue starts to form in to fill that space. Whether it's dense connective tissue or cartilage, it's going to fill in that area and start to reform the bone. The internal callus becomes a bony callus as that soft tissue starts to calcify. It becomes spongy bone, or woven bone as it's sometimes called, to fill in that space. The external callus will get smaller in the area but will not completely go away. The spongy bone is going to rearrange itself and rebuild the bone as it's supposed to be. At the edges, next to the external callus, the bone's going to start to form into the compact bone wall that we know of the diaphysis. And then eventually everything will get back to basically how it was. Connective tissue, when it's injured, will tend to try to grow back a little bit stronger. It'll lay down more collagen fibers and that sort of thing. When we see that, that's what we call a scar. So bones have scars in them too. Where a bone scar is, the bone matrix is going to be a little bit denser to make that part of the bone a little bit stronger. You can see that on an x-ray. Give it enough time, the bone scars will resorb back to their normal state. And by enough time, I might mean decades. Now, in the picture here where the break site was, you can see a little bit of an enlargement, which is going to happen. Eventually that will resorb back to its original shape. That's part of the healing process. Consider this question. When you feel that you've reached an answer, hit the next button to go into the next slide, which will reveal the correct answer. The cells that release calcitonin are called parafollicular cells. Now, it's important to keep this straight because there are structures in the thyroid gland called follicles that have follicular cells in them, and they make the other types of thyroid hormones. Parafollicular cells are the cells outside of the follicles, or around the follicles, and they make calcitonin. It's important, however, not to confuse parafollicular cells of the thyroid gland with cells of the parathyroid gland. They both use para, obviously, but they're referring to two different populations of cells in two different glands.